All right, picture this. You're in the hot seat, technical interview for a job you really want. The pressure's on, and they start asking you about the very heart of the operating system. Well, today we're going to crack the code on one of the toughest topics out there, Linux device drivers. So let's start with the most basic question of all. I mean, think about it. You write code, you click a mouse, you type on a keyboard, but how does that abstract world of software actually connect to the physical world of silicon and circuits? The answer, and really the hero of our story today, is the device driver. To get you prepped, we've laid this out like a roadmap. We're going to start with the lay of the land, then we'll actually build a simple driver, look at the tools you'll use every day, figure out how to fix things when they inevitably break, and then we'll wrap up with the single most important takeaway. Okay, let's dive into section 1, the lay of the land. Before we can write or debug a single line of code, we really need to get our heads around what a device driver is and, just as importantly, where it lives in the system. So what is it really? You know, at its core, a device driver is basically just a translator. The Linux kernel speaks a kind of general language, right? But your specific graphics card or your network adapter, it speaks its own unique dialect. The driver is that interpreter in the middle that lets them talk to each other seamlessly. Now, in the world of Linux, these translators come in 3 main flavors. You've got character drivers, which handle data as just a stream of bytes. Think of your keyboard. Then there are block drivers, which manage data in fixed-size chunks, which is perfect for hard drives. And of course, network drivers, which, as you can guess, deal with sending and receiving packets of data over a network. Okay, so where do these drivers actually live? I love this analogy. Think of your computer as a restaurant. User space is the dining room. It's safe, it's where your applications run, and if a customer spills a drink, it only affects their table. But kernel space? That's the kitchen. It's where the real powerful work happens. Drivers live here, with direct, privileged access to all the hardware. It's incredibly powerful, but if something goes wrong in the kitchen, the whole restaurant shuts down. And that, my friends, is a kernel panic. So, with all this hardware, how does the kernel even know which driver to call for which device? Well, it uses this simple but totally brilliant ID system, major and minor numbers. The major number is like saying, I need the USB driver, while the minor number specifies, and I mean the third port on the left. It's basically a unique address for every single piece of hardware plugged into your machine. All right, let's move on to section 2 and get our hands a little dirty. We're going from theory to practice now, and we're going to look at the nuts and bolts of creating a character driver, which is probably the most common type you're going to run into. Okay, pay attention, because in an interview, they are almost definitely going to ask you to walk them through this process. It's 4 key steps. First, you ask the kernel to give you some major and minor numbers. Second, and this is a big one, you define your file operations. We'll get to that in a sec. Third, you initialize the kernel's character device structure, or CDEF. And finally, you add that CDEF to the system so that your applications can actually find and use it. Now, if there is one thing, just one thing you remember from this section, make it this: the file operations structure. This thing is the absolute heart of your driver. It's basically a list of functions that you give to the kernel. It's how you tell the kernel, hey, when a user wants to open my device, call this function I wrote. When they want to read from it, call that function. It's the bridge. It connects what the user does to what your code does. And these are the big 4 functions you'll be defining. This should look really familiar, right? They correspond directly to the standard file commands everybody knows. You open a device, you read from it or write to it, and when you're done, you release it, which is basically just close. Your driver's whole job is to implement what actually happens for each of these actions. Okay, on to section 3. You've written your driver code, it's compiled. Now what? How do you actually get it into the running kernel? This is where your command line toolkit comes into play. You're going to use one of 2 main commands to load your driver, which is also known as a kernel module. insmod is like a scalpel. It's super simple and direct, but it's not smart. It won't load any other modules that your driver might depend on. Then you have modprobe. Modprobe is the Swiss Army knife. It's way more intelligent. It automatically finds and loads all the dependencies for you. Honestly, it's the tool you should probably reach for 9 times out of 10. But what about debugging? How do you print a message from inside your driver? You can't just use printf. Remember, we're in the kernel's kitchen now, not the safe dining room. Printf is a user space thing. The kernel has its own version called printk. It works in a similar way, but it writes its output to a special safe place called the kernel ring buffer, and it has some important limitations, like no floating point math, to make sure it doesn't destabilize the whole system.
So you've put a printf in your code. How do you actually see the message? It's simple. You just use the command dmess. This command literally just prints out the contents of that kernel ring buffer. When you're debugging a driver, printf in your code and dmess in your terminal are your absolute best friends. It's the ultimate duo.
Which brings us perfectly to Section 4, debugging driver disasters. Because let's be real, writing the code is only half the battle. Finding and fixing the bugs is the other half, and that is a skill every single interviewer is looking for. So let's play out a common scenario. You've compiled your module, you go to load it with insmod, and bam, it fails. The command just returns an error. What is the very first thing you do? Your first move, always, is to check dmess. The kernel is actually incredibly helpful. When something goes wrong while it's trying to load a module, it will almost always print a really detailed error message to that ring buffer explaining why. Maybe you forgot a dependency. Maybe you have a symbol conflict where a function in your driver has the same name as one already in the kernel. dmess is where you'll find the answer. Now for something a bit more serious. You check dmess and you see this terrifying message, null pointer dereference. Whoa, okay, this isn't just a loading error anymore, this is a crash. This means your driver tried to use a pointer that wasn't pointing to anything, which is a really critical bug to have inside the kernel. The key here is not to panic. You gotta be methodical. The dmess output, which is often called an oops message, will give you a stack trace that points to the exact line of code that failed. Your job is to be a detective. Trace backwards from there, use printfk to see what your variables looked like leading up to the crash, and figure out why that pointer was null in the first place. All right, let's bring it all home. Our final section, the key takeaway. After all this, what are the core principles you absolutely have to remember? Not just for the interview, but for your whole career. Okay, here it is in a nutshell. First, drivers are the fundamental bridge between your software and the physical hardware. Second, kernel space gives you incredible power, but it is totally unforgiving. Third, that file operation structure is the central hub for how your driver talks to the rest of the system. And finally, never ever forget that dmesseg is your #1 absolute best friend for debugging. So we'll leave you with this last thought. Mastering everything we just talked about, that'll get you through the interview for sure. But what comes next? What's the difference between a driver that just works and one that's truly elegant, efficient, and secure? Well, that's the question that takes you from being a good candidate to being a great systems engineer.